delay. The session will be one on ZK EVMs. My name is Orest. I work with Scroll, and we have several other Scroll team members here on the ground. If you have any questions later on, I see two more colleagues from Scroll here, so feel free to approach them anytime. Let us talk about UX. As we know, there's big UX issues in crypto, and I'd like to bring upon you a thesis today that ZK EVMs are able to help with our big UX showstoppers. And so what are those two UX issues I'm thinking? Number one is the fact that there's high fees in blockchains. This is something that looks a bit underwhelming by now, and everyone knows there's high fees, and we kind of have gotten used to the fact that there's high fees in Ethereum, and we have gotten to live with that. But if you think about user experience, UX, the fact that there's high fees has far-reaching consequences. And so one consequence is that very directly, people get to pay a lot, and so they don't use your product. But there's many more and maybe less direct consequences, such as because fees are quite high, developers invest into optimizing the smart contract for gas, rather than thinking about the business logic, like the user flow and the value add to the user. So many indirect costs to those high fees as well. And the other UX showstopper, in my opinion, is the high latency. And that becomes quite severe, especially when you come to think about user situations or use cases where the user needs to interact with a series of transactions on a blockchain, and maybe they require some sort of confirmation, maybe even some sort of finalization at some point. Maybe some of you have tried or succeeded at getting an ENS name. Anyone here has an ENS name? Hand up, if I may. Yeah, like a fifth of the audience here seems to have tried or succeeded at getting an ENS name. Depending on when you did that, you might have been faced with a multi-step approach that not only, where it would be an understatement to say the latency was high. In fact, you were probably asked to wait for 1 minute here, and then there was this delay, and you needed to refresh for a few minutes, and at some point you managed to get what usually in Web 1 and Web 2 would be an atomic step. And so, yeah, that's the other UX showstopper, high latencies. Now, what is a solution to this? Well, my theory today will be ZKPs to the rescue, zero-knowledge proofs. But not just that, but a combination of zero-knowledge proofs that you apply to the Ethereum Virtual Machine, the execution model behind Ethereum smart contracts, in the form of a rollup. And that's what we like to call the ZK EVM. And in fact, there's many ZK EVMs out there already that are being worked on. But then, this whole thing, the ZK EVM, needs to be understood by devs in order to solve for UX. The good news is the dev only needs to understand the ZK EVM as a black box. There's no need to understand the intricacies and the inner workings of it. And so the motto here that I'd like to make is, let us make DevX boring. And that is something that the crypto community has kind of avoided. It's kind of cool to have this new language. It's kind of cool to have those new features in your framework and in your stack. But it's easy to forget when you are this passionate young dev who wants to learn new things, that for many existing developers or developers who maybe know some stack, know some frameworks, this is a barrier to entry, and this is something that lessens the spectrum of available talent or available talent pool, available resources that are there to actually create those value-adding applications on a blockchain. So my point is, hey, let us try to make developer experience same as what people are used to already, rather than adding new features, and make the additional improvements opt-in and optional for the developers. And the cool thing here is this is just the beginning, and zero-knowledge proofs and ZK EVMs, but also other applications of zero-knowledge proofs come with a very cool perspective, especially when it comes to lowering latency in the mid and long term. There's a lot of cutting-edge research where we can see things that haven't been possible before because of this very cool property set of zkPs. We'll come to that briefly later, but for now we will be focusing on scalability and tackling the first UX showstopper that I mentioned, the high fees. And so let us talk about how ZK EVMs help to scale Ethereum and reduce fees, and where those terms that might be familiar to some but not everyone, how they come together: rollups, zero-knowledge proofs, and ZK EVMs. And so if we remove the words that are familiar to everyone, we are left with several buzzwords: ZK EVM, scaling Ethereum, rollups, and zkPs. And I'd like to get a quick show of hand. Who would be able to define each of these terms? Just to gauge. Okay, if we remove zero-knowledge proofs, anyone able to define those? Okay, if we remove ZK EVMs and zero-knowledge proofs, anyone able to define scaling Ethereum and rollups? Okay, that's like a third of you. Okay, so that's good. I will not be skipping my term explaining intro slides then. We can go through them. And feel free to stop me anytime. We have a helper over there. Thank you so much from ETH Barcelona volunteer team who has a microphone and will be able to give you a microphone for you to ask a question while I'm trying to convey some of the points going forward. Just please, that's a very, very big problem for a system that's supposed to support the world, that's supposed to work globally. But then again, is this an Ethereum problem, or is this a blockchain problem? Well, let's go further. I'm a computer scientist and not a blockchain scientist, and I like to think about blockchains as databases and see scalability as an intrinsic property of a distributed database that's supposed to have some desirable properties. And so in theoretical computer science in the 80s, we've had the CAP theorem that is basically a trilemma similar to the so-called blockchain trilemma that we like to talk about in the 2010s forward, which basically means there's three cool properties: security, decentralization, and scalability that a blockchain can have. Pick two of them. You can't have all three of them. And that's a very annoying situation to find yourself in. So what do you go for? Well, there's different scenarios. Ethereum decided to sacrifice scalability and keep security and decentralization. That's how Ethereum was able to basically have those security and decentralization properties, but it had to restrict itself to the 15 TPS that we mentioned earlier. Now, what alternatives would there have been? One alternative, alternative B, would be, hey, let's sacrifice decentralization. And that will lead us to a monolithic chain that has high TPS, which is possible because the nodes, the participants in such a network, are required to have strong, powerful machines, like server-grade machines. So we get scalability, we get higher performance level-fees, and we keep security, but we don't have decentralization. It will be a centralizing force. The alternative C, on the other hand, is we can sacrifice security to keep scalability and decentralization, leading us to some sort of multi-chain system. Now, did Ethereum really sacrifice scalability? There has been talks of L2s, but called slightly differently, even of rollups as early as 2014. 2014, that's 9 years ago. And it seems like this had been part of the original design, that there is ideas, there is hopes towards regaining some of the scalability element without sacrificing too much of the other two. And so L2s have very varying definitions. There's Twitter wars all the time about everything, including the L2 definitions, as we've seen recently. But basically, I think most people would agree that a layer 2 solution is some sort of scalability add-on to a base and blockchain, such as Ethereum, that inherits some of those desirable properties. And I would say specifically the security properties and potentially this decentralization as well, while making transactions cheaper. And so one type of L2s is rollups. Rollups were deemed as the end game by some people on Twitter some time ago already, and they have been increasingly popular recently. And you might have even used an optimistic type of rollup to come here today to get your ticket. And the optimistic rollups are one type, and the ZK rollup is the alternative. So let's briefly talk about them. Well, the optimistic rollup, such as Optimism or Arbitrum, has this economic incentive assumption that people will not cheat, because if you prove someone cheated, you will be able to penalize them and get a reward. And so they are easier to implement, easier to create adoption for, and also simpler when it comes to implementation in technical terms and mathematical terms. But that is already kind of stretching it. The optimistic rollups we have out there, they don't really, they still have a lot of training wheels, and a lot of the constructions that are required for a rollup aren't really implemented yet. So that's something to keep in mind when we say, hey, optimistic rollups are simple. The drawback they have, on the other hand, is that they require a long time during which an actor can challenge a potentially malicious participant in order for this economic incentive to work. And so this can't really be worked around. And this is usually 7 days these days. And so this leads to a delay when you want to get out of the rollup. So the alternative is zero-knowledge-based rollups, ZKP rollups, also known as ZK rollups. And the problem is, in the name already, these rollups are not a privacy-preserving type of rollup. Those are called ZK rollup, to make things more confusing. ZK rollups are general purpose, can be a general purpose rollup as optimistic ones. They just have a different way where participants convince others about the state of the world in a rollup. They don't have the economic incentive, but rather there's this cryptographic primitive combined into a zero-knowledge proof, which basically makes it such that other people can trust what you claim without re-executing to get to the same conclusion. And so the problem with them is they are more complex, even more complex to build. They are even less popular in terms of adoption. You could not have gotten a ticket to this conference using a ZK rollup. But the advantage is that the finality on the L1, on the base layer, on Ethereum, can be a lot faster. So how do they work? The black box view, again, is, well, like a gray box view, is usually in a blockchain we have this approach where we re-execute transactions created by other people to convince ourselves, hey, this is what the world looks like after I have taken into account what others are telling me is happening. And that's what everyone on the network is doing continuously. That's how we can have this shared consensus about what is true, about what the state of the world is, without trusting each other. Now, as you might notice, the problem is if we have one additional transaction, one additional actor in such a network, every other participant is impacted proportionately to that additional transactional actor. So that means if we want to have twice as many people, or 10 times as many, each and every actor will be impacted in 2x or 10x. So like that's the definition of a non-scalable system. You add more, and the cost grows linearly. And so in a ZK rollup, we replace the tree execution with a zero-knowledge proof that has this property that it certifies to other people that this transition into a new state, into a new idea about what the world looks like, without them needing to re-execute the transactions that led to this new state. And in particular, is this proof smaller and faster to verify than re-executing the transactions? And that is mind-blowing. That's what is so weird. Like, how can you possibly convince someone about the new state and convince them without having to trust each other in a way that's faster than having to re-execute the input? Like, that's very surprising to, like, when you come to think about it for a while. And the other advantage is that the prover, so the entity creating such a proof, not even the prover needs to be trusted. And so, in particular, does this mean that we can add more user transactions, so more users to the network, more nodes, and the cost per node doesn't grow linearly, it grows sublinearly, it just grows a bit. So that's what we like to call scalability. Any questions to this end? Okay, so what types of ZK rollups are out there? Well, I mentioned ZK rollups can be application agnostic, but they can be application specific as well. In fact, application specific rollups, such as transactions only, have been around for a bit longer. They are a bit easier to implement. But what interests the community the most are application agnostic, general purpose rollups, and this is what we call the ZK EVM or the ZK VM, depending on how compatible with the EVM such a rollup is. And so this is where it gets a bit more technical. What does it mean to be compatible with the EVM? What is the EVM in the first place? Well, again, if you think about the EVM as a computer scientist, you will just imagine that we have this problem. We want to have different people in the world process some transactions and come to a conclusion that is consistent. But one person will be using an ARM processor and another will be using Intel, and one person will be using this operating system that has this definition of number, length and bit, and the other one another one. And so to standardize this execution, that's why we introduce a virtual machine as a model for basically a standard way of dealing with transactions and getting to the output. And so Ethereum Virtual Machine is just that. It's just a virtual machine. And a virtual machine works as follows. It takes as input some programming language. In the case of the EVM, it's Solidity or something similar, like Viper or Yule. This language is then transferred to an intermediate representation, the IR, which is basically a bit similar to the language itself. And that thing is then compiled to bytecode. Bytecode is are the instructions that are getting executed within the virtual machine. Those are those standardized instructions that everyone will be executing in the same way because they have the exact same definition of how a given instruction of code is to be treated. And so in order to achieve that, we have several components in our EVM. So we have this executor engine, but we also have a stack. So a stack is a way to store state, store data. That's one way of having memory. And we also have a more traditional memory component where you can store data as well. And we have the state machine itself. So that is like the theoretical model of what happens when this input and that input have some values. What state do I go into? This is not the state that we talk about when it comes to Ethereum. This is the state machine of the EVM itself. And then, of course, the storage, where you store, for instance, your code. So why are we talking about this? Well, it gets more complex than this. To understand what a ZK EVM is and what the differences between the flavors are, Vitalik came up with this diagram that has 5 types in it. And to make it more confusing, he actually called them ZK EVM type 1, 2, 2.5, 3, and 4. These are the 5 types. And the idea is basically, depending on where in this EVM you start, like where you cut off. So for instance, if you have a language level ZK rollup, you basically take the language, solidity, or the IR, and you cut out the bytecode and the runtime components. You replace them with a system of your choosing, and you hope that this system behaves similarly enough to the EVM. And then, if you have a bytecode level ZK rollup, you keep these, you take just the EVM bytecode as input, and you just will have replaced the runtime component by something that is ZK EVM or ZKP based. And so that's where these types come from. And the interesting 2 types I think that I just mentioned are type 2 and type 3. So language level compatible and bytecode level compatible with some nuances. Feel free to read it up if you're interested. Vitalik has a blog post from last year about these. And so asking ourselves, why is this only possible now if the ZK EVM has so many advantages? What is the cost? Like, what's the problem? Well, if you think about the axes, you will see there's this compatibility with the EVM axis, but there's also the performance axis. And being highly compatible with the EVM, like ZK EVM type 1, comes at the cost of being extremely unfriendly when it comes to ZKP operations and computationally very expensive. And so that leads to the prover having to do a lot of hard work to create a proof. And that also means that your engineers will be faced with an even bigger challenge in a very complex product that they need to build. And on the other hand side, ZK EVM type 4, which no one really wants to be, but as several teams currently are, comes at a pretty low compatibility with the EVM, so they can't benefit from the EVM ecosystem that well, but it's way easier to get the computational capacity to get those proofs done in a reasonable time. And also, it may be easier to implement. So why is it possible now? What's changed? Why haven't we done this from the get-go when Ethereum was first implemented? Well, there have been a few changes since. So first of all, those zero-knowledge proof systems, they have been around since the late 70s, But it's only the recent years that improvements were made to how systems are actually built and implemented in practice that led to orders of magnitude of performance improvements. Second of all, we've seen great hardware acceleration improvements where we can parallelize parts of the proof generation, use GPUs or even specialized hardware, and that gives us another few orders of magnitude of an advantage. And lastly, we just are benefiting from the fact that ZKPs are trendy. And people are investing millions and billions into ZKPs, and very clever people are looking at them, but also they are trendy amongst the open source community. People like to deal with hard and interesting maths and engineering problems. And if you combine this in a collaborative way, you get to, again, have orders of magnitude of improvement. And so from a ZKP that would have convinced other nodes in 2013 about the state transition correctness, and that would have taken maybe 100 years to generate for every state transition. We are now at about 10 minutes, and that's pretty valuable when it comes to practice. Any questions so far? Okay, so where is Scroll in this whole puzzle? Why is Scroll even here? Well, so we are building towards a ZK EVM type 2 according to Vitalik's classification, and that basically means we will be taking bytecode from a compiled solidity to intermediate representation code and putting it into our runtime component and creating a proof for that and submitting those to Ethereum. Why are we doing this? Why be bytecode level compatible? Why not language level? Or why not ZK EVM type 1? Well, it's a trade-off, and the benefits of being a type 2 are that you get to benefit from most of the EVM ecosystem. So not only can you take existing smart contracts code and dApps and put them in the rollup, but you can even leverage existing developer tooling. And so, for instance, a debugger that depends on breakpoint settings and at some bytecode line will continue to work as they've always used to. At Scroll, when we first set out on this journey, we literally forked Ethereum's client and ran it with some varied parameters, and we were still able to attach a block scout, block explorer to that network without any modification to block scout. In fact, to this day, we are running a block scout Docker container compiled for Ethereum that we didn't even recompile, and that is running on our L2. So that's a big, big advantage in terms of tapping into the cool critical mass that Ethereum amassed. Second, it does encapsulate this complexity of ZKP very well, and it makes it such that the developer experience can be boring. You don't need to know anything about ZKPs. You use your Solidity or your Viper, whatever you like, but also your opcodes from Ethereum, just as though it was Ethereum itself. And third, we get to benefit from most of the EVM execution model trust and security assumptions. That makes audits and security considerations very favorable. So yeah, we are trying to keep developer experience boring. That is our goal. And to that goal, we are shortly before a next announcement. It will not be a mainnet. We actually will be launching a further testnet very soon that will be settling to Sepolia. And this will be a long-lived testnet that will stick around for a long time. And very soon after that, we will be launching our mainnet. So there's a couple of to-dos for mainnet still open, and we are making steady progress on them. We are still in the process of dealing with uncommon errors, corner cases in our circuits. We are still working on finalizing precompiled support, and we will not be launching with the hash, with the 3 hash precompiles, but the other precompiles will be supported in like 99% of the use cases. And other than that, we are still working on finalizing the security audits and optimizing code for performance. The vision with the whole thing is to work on EVM equivalence, work on the developer experience not being the USB, but being boring, but also to work on decentralization. And we are already seeing a distributed prover network that we will be decentralizing soon after mainnet launch. And right after that, we'll be working on getting the sequences decentralized as well. And we are trying to achieve that while working very closely with Ethereum Foundation. If you check our repos, you will see, or actually if you check Ethereum Foundation's privacy and scaling explorations, PSC's repos, you will see that I think amongst the top 20 contributors, oftentimes half of them is actually people from Scroll. So we are very proud about that. So where's the catch? Well, there's actually a twofold catch. And the direct catch, of course, is the computational cost to create proofs, as we've seen before with Vitalik's chart. But the meta-level catch is not less important. That's the complexity of building such a system. And this is something that is hard to overstate. And so to make it maybe a bit more clear, I'd like to show you some challenges that we ran into while building the system. And feel free to interrupt or ask questions if you have any. So first of all, what you need to do when building a ZK EVM rollup is you need to actually create those ZK circuits. Second, you will need to turn them into a virtual machine that behaves like the Ethereum Virtual Machine. And last, you will actually want to also communicate with Ethereum mainnet. That's what makes you a ZK rollup in the end. So let's talk about why it's hard, what the challenges are when building a ZK circuit. A ZK circuit is a different way of thinking about the program from what you might be used to. Usually, you have a program that takes some inputs, does something on them, and outputs a new value. Now, a ZK circuit behaves more like a logic gate, you could think, in that it has the inputs and the output, like the presumed output as an input. So it's very confusing. It has everything that will happen around your program as input, and what it outputs technically is whether this constellation is valid or not, whether this set of input and output values is an allowed configuration of the circuit. And so it will output valid if the third input equals the real input of these two values in a normal program, and invalid if it's something else. And so it's very important when thinking about ZK circuits to not think step by step, like imperative programming wise, but rather to know what you are actually doing is you are actually running your normal program. Like your EVM is running the transaction, and you know what the output is. And it's only once you know the inputs and the outputs that you try to trick into making them into a circuit, such that the circuit only outputs valid if it's a valid combination of inputs and outputs, and invalid otherwise. That's basically the trick. And so there's a couple of technical intricacies to it. One intricacy is we don't deal with executes those transactions. This is the regular EVM world. This is not the ZK world. But then it also needs to have a component that listens for events on the base layer in order to have this communication flow, and the same for the other direction. So we have those additional two components in our sequencer node. Then, in order to convince people on the base layer, we also need to have those proofs, right? This is just the EVM, like an EVM-like node. So we need to have a prover that will be creating, that will be getting execution traces, so like the interim results of the execution of the transactions, and proving them and submitting them back. And ideally, we want to have it in a distributed and later decentralized fashion, those provers. But now, we care about decentralization, so we don't want to have a single sequencer. We also want to have sequencer decentralization such that each and any actor may join the network and be able to also talk to the bridge contract and the rollup contract on the base layer. And this is actually something that is a hard problem and where a lot of research is ongoing right now. That I think that there might be some other talks about sequencer decentralization at this conference. So yeah, that was basically a quick run through the challenges in building a ZK EVM. We are having some bounties at at the hackathon here in Barcelona, so feel free to convince yourselves for how boring it is to deploy to scroll. There's a bounty specifically dedicated to you taking our demo code. I just tested it 1 hour ago. It still works. You take our demo smart contract with hard hat or Foundry or whatever you like, hit deploy while having exchanged the RPC endpoint for scrolls, and it just works. So it's very, very boring, but I think we have a pool prize for projects that deploy to scroll. That's the criterion. Is that correct? Do you guys know? Yeah, so it's correct. We have some other bounties as well. All the details are on the website, linked here. Okay, any questions? We have a few minutes for Q&A if there's any questions. Yeah? But please, if you could speak into the mic.
Yes, okay. So I was looking around the field and there's Polygon, ZK EVM, there's ZK Sync. How does Scroll compare with those?
Yeah, so I haven't refreshed the slide, so it's a bit old, but basically it's how compatible with the EVM you are. So yeah, this is up to date, Polygon is called Polygon ZK EVM now. They are quite similar to us. They have a slight technicality in terms of how they prove, or like how they run the virtual machine. ZK Sync is very easy to distinguish because they are a language level ZK EVM. So it means you can recycle your smart contract, but you can't recycle your bytecode. And so that means you need to have a specialized version of Foundry. You need to have a specialized version of hardware. You need to have a specialized debugger that works with this ZK bytecode rather than the Ethereum bytecode. And then there's Starkware that where you are required to actually rewrite your code in a separate programming language. And they have been working for a while on a Cairo to Solidity translator. I think it doesn't work that reliably yet, but if they get to it, that would make them a ZK EVM type 4.
I have a few other questions, so if no one else, then I'll just keep going. So, do I understand, so finality in 10 minutes right now, because it takes 10 minutes to generate a proof? Did I get that?
I wish.
No, that's not how it works.
So, okay, the order of magnitude is 10 minutes. In order to come up with a proof, depending on what your parameterization is, so for instance, there's actually way more challenges than what I've shown. So for instance, one challenge that every ZK EVM, as far as I know, is facing right now is, hey, we have those circuits, but those circuits, they are fixed in size. You have to decide and commit to a size for your circuit up front. And that means that you can only ever fit a limited number of operations into your circuit. And the problem that others and us are facing is we need to choose these values such that we are able to prove even very complex and ZK unfriendly transactions without blowing the overhead too high up in terms of the normal use case, the average case scenario. And so depending on how you choose them, you might end up with a 5-minute or 5-hour proving time.
So it depends even on the opcodes that you use.
Well, opcodes and various restrictions. So for instance, do you allow for pre-compiles in terms of can I have just a very, very ZK unfriendly and so expensive hash precompile spammed throughout my smart contract or not? But then there's other levels of delays. So for instance, once you've created the ZK proof, you also want to submit such a ZK proof back to the base layer, so Ethereum, and the base layer needs to validate this proof. That takes some time, that takes some gas, depending on how aggressively you do it. So maybe how long you wait to aggregate maybe more transactions before you submit to the L1, or how long you wait if there's maybe a congestion situation on the L1 that will impact your finality. And then the boring but important security thing. Like if you notice, if there's actually a cool website called rollup.codes that puts numbers on rollups in terms of, for instance, finalization. And so what some people are doing is they artificially add a time lock to the finality on the L1 so that because all of these systems are new, right? In case someone managed to find a loophole and abuse it, the team behind the rollup can still pull an exit hatch trigger. And so they artificially increase it to, for instance, 24 hours. Many things like that to consider.
It's almost like gas limit, is it? Or
yeah, so actually rollup.codes contains explicitly also the gas limit that people are allowed to have, like per block and so on. There's all sorts of parameters that need to be picked wisely and that impact the overall resulting fee structure. So if you read Vitalik's estimates, when it comes to how much are we saving with a ZK rollup, it's between 10x and 10,000x. Depends.